Good afternoon. My name is Ronald Portoreal. This is Matthew Koza and Sean DePascal. We are the MiningMECPanters, and our project is the NASA Lunar Robotics Project. The purpose of our project is to design and build a mining robot that can traverse the lunar soil. We have a weight limit of 80 kilograms. We have a design limitation of 1.5 meters by 0.75 meters by 0.75 meters. We have a data cap of 50 kilobytes per second. We plan to implement a hybrid design in which we'll do a fully autonomous with a manual option. And we have a dust tolerance in which we need to protect our components. Here is the schematic of the terrain in which we will compete. Two teams will compete simultaneously. The craters that will be randomly scattered, and there will be 30 centimeters max depth.
Some of the design considerations that we took into account when designing the rover were the mobility system, whether we wanted to use wheels, treads, legs, or a hybrid of any two. Also the collection mechanism, whether we wanted to go with a scoop design or a continuously operating conveyor belt type design, as well as the deposit mechanism, how we would transfer the collected regolith into the depositing bins located on the field. And also our control systems, whether we wanted to use sensors, cameras, or any combination, as well as how they would adhere to the data transmission limitations.
To move our rover, we considered a couple of different mobility systems. The first were the wheels. They'd be the cheapest and easiest to implement, but will give us the least amount of traction. We then considered adding some links to the wheels to add to the traction, but it would also increase the weight and the cost. Ultimately, we decided to go with a track system, which would be the most expensive and allow some dust into the system, but it would give us the most traction.
For the collection mechanism, we had two options. First, a conveyor belt system. This system has a higher cost, but the advantage is that it has continuous pickup. The next is a scoop system. It has a lower cost, but requires more power and has a limited capacity.
Some of the design changes that we made from our initial design to our current design, we shortened the frame length by roughly 12 inches overall. We switched to a thicker frame material. It went from 16th inch wall to 8th inch wall 6061 2x1 box aluminum. We added a support frame for the collection bin, as well as moved the collection mechanism outside of the footprint of the rover. And we also switched from gear-driven output shafts to the mobility system to sprocket-driven. Finally, we switched from individually sealed and enclosed gearboxes and motors to open design. This will allow us to incorporate them all in a single enclosure, so that way we can service the rover easier in case any mechanical failures occur.
Using SolidWorks, we ran a static loading test on the base of our frame. We applied a load of 1,200 newtons, which was our goal, and used the von Mises stress criterion. The simulation gave us a factor of safety of 9.9.
Here's the global component. It is split up into three parts. First, the global awareness. 50 teams will compete internationally. And at the beginning of the semester, we did a case study of several teams to see what they previously had done. Second is global perspective. The lunar soil can be used to harvest energy, and this potentially will set up the groundwork for future colonization missions. Lastly, the global engagement. 50 teams will show different solutions to the same problem. And additionally, our team is a multidisciplinary team of 3 mechanical, 3 electrical, and 2 computer engineers.
This is the timeline for our project. It starts in August and ends in May, which is when the competition will take place. What you see in orange is what's being completed, and the green is still pending.
This is a cost analysis that we did, an estimated budget showing the individual prices of the components and materials that we have purchased or plan on purchasing in the future. And altogether, it gives our project a rough budget estimation of just over $5,000 for everything. This is a list of references for all the pictures and figures that we use throughout the presentation. And are there any questions?
Let me start off. You mentioned that there are other team members. Are they here today?
They are not here today, no.
Okay. And what was the division of labor, including their inputs?
Well, for us, we focused primarily on the mechanical ends of things. The electrical guys are taking care of the calculations for the motors, as for what speed controllers we need and the battery requirements, as well as incorporating sensors in the future. And the computer engineers will be focusing on the autonomous design of the rover and using the sensors within the programming of it. And altogether, we've been working hand in hand with each other to make sure that all the components fit together nicely in the mechanical design and everything operates well together, so there's no panic at the end if something doesn't fit.
Also, the criteria for them joining our team was that they had to perform a fully autonomous robot. If not, the team would not be able to be put together.
Okay.
You had a slide that showed 3 boxes of your choices of metal and, there you go,
This one here?
well, actually, one in front of that, please. You changed your materials
Correct.
based on what failure and what criterion did you use for selection for the replacement material?
The major criterion actually was the availability of the material. We were having a hard time finding the 16th-inch wall 2x1 box aluminum, and the cost is significantly lower switching to the 8th-inch wall. And on top of that, the analysis that we performed for the stress analysis was with the 8th-inch wall, so it provided us with an ample factor of safety for that.
Okay, so it was cost was your primary driver of switching?
Right.
Okay.
Cost is our primary design.
Students, I get that. May I ask why you put the electronics out in the back and removed it from the main portion?
One second. This portion back here is going to be where all of the electronics are housed, and the gearboxes as well are going to be located in the back there. You can see this is the sprocket there that the gearbox will be driving with the chain.
And on your earlier design, it was in a different position?
It was spread out throughout the entire landscape. Actually, since with that one there, the collection mechanism being within the footprint limited our electronic space, and actually what we just did was shorten the frame so that way the collection mechanism is outside. It allows us actually for the same amount of space for the electronics, but we just switched to a individually sealed unit instead of having individual components sealed, so that way we could service everything in case of failure. Yes?
On the tracks themselves, are you driving more than one of those pulleys?
Originally, we were planning on driving 4 of the pulleys, but then the electrical engineers informed us that there would be some issues with obtaining adequate batteries if we would be driving all 4 of the pulleys without combining them into a single gearbox on each side. So currently, we were reworking the motor calculations to see if we could drive the rover using just the 2 pulleys located in the front of the rover. That's going off of total tractive effort calculations we obtained from University of Florida.
So there'd be one on each side, basically.
One
driving.
drive pulley on each side, yes.
One drive pulley. And if that drive pulley is not on the ground, if that's up in space and it's re-spinning?
Well, the pulley itself is actually a sprocket-driven pulley, as opposed to like a pulley and belt system, where the treads itself have holes that are located in a pattern on them, spaced out. So the pulley is actually going through the treads, so even if that section is up in the air, it should still drive it without issue. That was the main reason we chose that
But you've
design.
only got sprockets on 2 of the 4 pulleys?
We recently switched the, I'm sorry, what was the question?
Well, I'm questioning because basically the 3 pulleys in the middle are just there to hold space.
They're idler
Yeah.
pulleys. They weight distribution.
Okay, so if this is sitting on irregular ground, you don't have a problem. If you try to make a turn on irregular, this isn't going to be an issue.
It shouldn't, considering the surface that we're on. The terrain that we're on is very low density. So if we try to turn in place, there will be additional traction because there's no offset in the middle. But we should be able to still turn in place without issue, given the amount of torque that we have.
Any other questions? No?
All right.
Okay.